What's up, my stat stars? Michael Princhuk here, ready to start helping you prepare for the AP Statistics exam in May. Now, in this video, I want to walk you through some problems, multiple choice problems that deal with statistical inference. I'm going to combine proportions and means in this video. Again, that's Unit 6 and Unit 7 from the course exam description. Now, these questions in total are going to make up around 20 to possibly as high as 35-40% of the exam questions. So let's start taking a look at them now, but I want to tell you first that you're not going to see these exact same questions on the actual exam in May, but you will see ones very similar to them. Now, there's lots of different inference procedures. We got 1 sample intervals, 2 sample intervals, 1 sample test, 2 sample tests. So in this video, we're going to cover a couple of them, but making sure that you understand the key concepts and ideas from these questions is going to be vital to helping you prepare for the exam in May. All right, let's start taking a look at them now. Before we start looking at some multiple choice examples over statistical inference for the AP Statistics exam, let's take a look at what's on the formula sheet that can actually help you when it comes to inference. Now, there's 2 big inference procedures that we use in AP Statistics. Confidence intervals are used to make a judgment about what the population parameter could be, and a significance test is used to determine if there's significant evidence of a claim about that population parameter. Now, here is what is given very generically. The standardized test statistic that you would need for a significance test, this is going to be your t-score or your z-score, is going to be a statistic, something that you gathered from your sample, something that you actually observed, minus the parameter that we thought to be true, divided by the standard error of the statistic. And then for a confidence interval, the most generic formula possible to construct a confidence interval is taking a sample statistic plus and minus the margin of error. Now, the margin of error is a combination of 2 things. It's your critical value. It's going to be your t-score or your z-score, multiplied by the standard error of your statistic. Now, critical values are t-scores and z-scores that come from either invert norm and invert t that are based on how confident you want to be. And then the standard error that is going to be used, which is also used in the denominator of your standardized test statistic, comes from, well, different formulas based on proportions or means. And that's what's on the next page of that formula sheet. So there's a box here for population proportions, and we see here that for the standard error of a sampling distribution, we have a formula right there for 1 sample, and then here is the formula for standard error for looking at 2 samples and the difference between them. And on the next page, we also have means, and we have here the standard error. Look, it's perfectly labeled standard error of the sample statistic for 1 sample mean, and then we have the standard error for that sampling distribution for the difference between 2 samples. So again, all the formulas that you could possibly need are going to be in the formula chart or the formula sheet. You just got to kind of know where to look to get them. All right, let's start taking a look at a couple problems right now. All right, in this first problem, it says when conducting a large sample test with a null hypothesis that P equals a population proportion, I don't know, let's just make something up there. Let's just say that it equals 35%. P equals 35%. That'd be our null parameter, right? Our null proportion. Now, the test statistic is given by Z equals our sample proportion P hat minus that null proportion that we got from the null hypothesis divided by the square root of P sub 0 times 1 minus P sub 0 all divided by N, where P hat is the sample proportion. Which of the following best explains the justification of the denominator of this test statistic? Now, the deal here is that when we conduct a significance test, we have to assume that the null hypothesis is true. So if we're going to assume that the null hypothesis is true, we can actually calculate standard deviation. So remember, the formula for standard deviation, or standard deviation using our letter sigma, of a sampling distribution is the square root of P times 1 minus P, messy handwriting there, all divided by N. Now, we have to use standard error of our sampling distribution when we don't know what P is and all we have is our P hat. So we use the same formula, but it's going to be P hat times 1 minus P hat divided by N, all inside that square root. But the idea is this. In a test, we have to assume that the null hypothesis is true. So that means we believe, in this particular example that I just made up here, that 35% is true. And if that is in fact true, then we can actually actually calculate the standard deviation using that assumed to be known true value. So the answer to this question is going to be D. That denominator is the way it is because we assume that we know the standard deviation if we have to believe that that null hypothesis is true. So kind of a tricky question, but hopefully that makes sense. Now, this is only done in a one sample z-test for a population proportion. And again, it goes back to the idea that we assume the null to be true. In any other situation, we do divide by the standard error of the test statistic. All right, question 17 says a large sample 98% confidence interval for the proportion of hotel reservations that are canceled on the intended arrival day is 0.048 to 0.112. So again, we're 98% confident that somewhere between 4.8% and 11.2% of reservations are canceled on the day of arrival. What is the point estimate for the proportion of hotel reservations that are canceled on the intended day from this sample was constructed? Well, here's the deal. The point estimate is the dead center of your interval. The point estimate is your statistic. In this case, that statistic is going to be a sample proportion p hat, but in other cases it could be an x bar, a mean, or it could even be the difference between two sample proportions or the difference between two sample means. But in this particular one, the point estimate is the statistic that's dead center in the interval. So all we have to do to find it is take 0.048, add 0.112, and divide by 2. I mean, that's how you find the dead center of two values. You add them together and divide by 2. So that's going to be 0.16 divided by 2, and we get 0.08. So that means our sample proportion p hat must have been 8%, and then we add and we subtract our margin error from there to construct this interval. So the choice there would be C. This question says, based on a survey of random sample of 900 adults in the United States, a journalist reports that 60% of adults in the United States are in favor of increasing the minimum hourly wage. Now, let's just stop right there and gather what we have. So we got a sample of 900 adults, and from that sample, we know that the proportion that are in favor of increasing the minimum hourly wage is 60%. In fact, I'm shocked it's not higher than 60%. All right, if the reported percent has a margin of error of 2.7 percentage points, so our margin of error is 0.027. Which of the following is closest to the level of confidence? All right, so where is level of confidence? How is your level of confidence incorporated into margin of error? Well, remember the margin of error formula is this. It is the critical value, in this case that's going to be our z star, times the square root. Now again, it's working for proportions here, so this is working with the square root of our sample proportion p hat times 1 minus p hat, all divided by our sample size n. This is the formula for the margin of error when it comes to working with a single population proportion. Now, what do we know here? We know the margin of error is 0.027. We don't know the z star. But remember, the z star is directly linked to your level of confidence. If we were working forwards here, the level of confidence is how we go and get our z star. So that's actually what we don't know that we want to find. And then everything else we do know. We do know that our sample proportion p hat is 0.60. The opposite 1 minus p hat is 0.40, all divided by our sample size of 900. Now, this is our standard error of our test statistic, or the standard error of our sample statistic. So we can actually calculate that and then divide it over. So if we take the 0.027 and divide over by that square root of 0.60 times 0.40 divided by 900, we can actually get our z star. So go ahead and do that math if you want, but that gives you a z star of 1.653. Okay, that's great, but how do I find my level of confidence based on that? Well, remember how we get z-stars working forward. If we construct that sampling distribution, right, our level of confidence is where we're expecting the majority of samples to be in the middle. And our z-star is our critical z value for where those interval, where that center proportion, that center area begins and ends. So that's exactly what the 1.653 is. So this would be negative 1.653, and this would be positive 1.653. And in between there is our level of confidence, the percentage of sample proportions that are going to be so close to the mean that the confidence interval will capture them. So again, how do we find that area in between those two z-scores? Well, we're just going to go ahead and get our calculator to do it for us. We're going to go and hit second vars here to get to our normal CDF. Normal CDS can find the area in between two z-scores. So we're going to look from negative 1.653 to positive 1.653. And that's going to get us a area of about 90%. So there's our answer, about 90% confident. So if we were 90% confident, that would produce a z-star of approximately 1.653, and then that would in turn get our margin of error. So this is a really good problem. In fact, this particular year on the AP exam, this was a very challenging problem that a lot of kids got wrong. They just weren't quite sure what to do because it's not a very common question. And even as an AP Stat teacher myself, we don't typically cover a problem like this in class. But it's all about working backwards and thinking, where is the level of confidence at in the margin of error formula? It's right with that z-star. That z-star is how we get that z-star from our level of confidence. So now all we're asking you to do is work backwards, get the z-star, and then use the z-star in reverse to figure out what your level of confidence is. Pretty good problem. All right, in this problem, when using a one sample t procedure to construct a confidence interval for the mean of a finite population, a condition is that the population size be at least 10 times the sample size. The reason for the condition is to ensure what? So basically, one of the conditions that we kind of just get used to checking is that our sample size n is less than 10% of the population. But why? Why do we have to do that? Well, here's the deal. We need independence. Our formula for standard deviation when it comes to sampling distributions will not work unless we have independence. And the only way we can guarantee independence between our samples is if we sample with replacement. We get a sample, we put it back before we get our next sample. In the real world, that's just not really ever going to happen. We typically sample without replacement. Now, when you sample without replacement, you immediately violate independence. And that is kind of like a problem. But here's what we say. We say, well, listen, if the sample size is small compared to the population, then that degree of dependence, because if we're not independent, we're dependent, is negligible, and we can still assume to be independent. So that's where the 10% condition comes in. If we say our sample size is small relative to the population, and the rule is under 10% of the population, then yes, we technically do not have independence, which means our samples kind of depend on each other, but that degree of dependence is just negligible. It's not a big deal as long as we are under that 10%. So that's exactly what the answer is going to be here. It's going to be choice D. The degree of dependence among observations is negligible. That's why we have to check the 10% condition to ensure that, yes, we know that we're not going to have independence when we're sampling without replacement. But it's okay. The difference is negligible, and we can still assume independence for our samples. Kind of a tricky question, and sometimes it's hard for a lot of kids to understand that 10% condition. So again, just trying to quickly going over in this video. Hopefully that makes sense. All right, suppose that on a hypothesis test for a single population mean, we have an alternative that mu, the population mean, is less than 10. Assume that the alternative is true for a fixed sample size and a significance level alpha. The power of the test will be greatest if the actual mean is which of the following? Okay, so here's the deal. Our alternative is that the truth is less than 10. The true mean is less than 10, and we are assuming that that is true. Now, how do we get more power? The two biggest things that I teach in class about how to get more power are bigger sample size and, well, higher level of significance alpha. But this is saying if we keep those the same, if we keep our sample size fixed, we keep our significance level fixed, how else can we get power? Well, essentially, the truth is that it's less than 10, right? The alternative is true. The true mean is less than 10. But the further we are from 10, the easier that will be for us to see and give us more power. Because power is making the correct decision. If the alternative is true, we want to say that the alternative is true. That's power. So the idea here is that if it's really less than 10, the further from 10, the more likely we are going to see that and hence reject the null and go with the alternative. So the correct answer here is going to be A, because 8 is the one that is most below 10. 13, 11, and 10, I certainly don't want to choose because, again, it says right here the alternative is true. If the truth is 10, 11, or 13, then the alternative is actually not true. Now, 9 is also less than 10, but 8 is more less than 10, if that makes sense, right? And when something is truth is way less than our thought to be null hypothesis, then we have more power to hopefully see that. So bigger sample size gives more power. Increasing your significance level gives more power. But if you also are further from the null, and if the null is that, we would assume here that the null is that the mean equals 10, the further we are from 10, the more likely we are to reject 10 and go with the alternatives. That's why we want to choose the answer of 8 here. A random sample of 50 students at a large high school resulted in a 95% confidence interval for the mean number of hours of sleep per day of 6.73 to 7.67. Which of the following statements best summarize the meaning of this confidence interval? Now, first off, what we typically teach kids in class is how to interpret the interval. So here I would say I'm 95% confident that the true population mean amount of time, number of hours that students sleep per day, is somewhere between 6.73 hours and 7.67 hours. But this particular question, if we read these choices, none of them really say that. Like some kids will jump to C and say 95% of the students in the survey reported sleeping between 6.73 hours and 7.67 hours. No, not at all. Wait a minute. If it's talking about the number of students in the survey, I know the number of students in the survey because I surveyed them and got the data. So it has nothing to do with 95% of the students. So that's immediately going to be correct. And then D says 95% of the students in the high school sleep between 6.73 and 7.67 hours. No, I'm 95% confident that the true mean sleep for the kids in the high school is in that range, but it's not about 95% of the students. That's incorrect as well. And then E says a student selected at random from this population sleeps between 6.73 and 7.6 hours per day for 95% of the time. What? No, that's nothing to do with you should have been taught. Has nothing to do with 95% of the time. That's incorrect as well. So now we're down between A and B. So here's the idea. This interval came from R1 sample. That's it, right? We're 95% confident that the truth is somewhere in this interval. Now, other samples would create other intervals. And every interval is going to create it, every sample is going to create its own interval. And we know that 95% of all possible intervals out there from all possible samples out there are going to contain the true population mean number of hours of sleep per day. So if I look at choice B, that's exactly what B says. About 95% of all random samples of 50 students from this population will result in a 95% confidence interval covered the population mean number of hours of sleep per day. Now notice how that didn't even mention our interval because our interval is our interval. So A uses our interval and A says 95% of all random samples of 50 students from this population would result in a 95% confidence interval of 6.73 to 7.67. So basically they're saying that, 95% of all possible intervals are going to be just the exact same as mine. Well, that's not true at all. Every sample is guaranteed to produce its very own interval. In fact, our interval is just ours. It's not going to match up with any other interval that's out there of the same sample size. So again, we know that we're 95% confident that the true population mean is in our interval. Okay, that's awesome. But what else does a confidence interval mean? It's basically saying, hey, listen, there's many, many, many other sample means out there, and every one of those is going to create its own interval, and 95% of those intervals are going to create or cover or include the population mean. That's exactly what B says. So B is the correct answer there. All right, in this problem, this is a random sample of 432 voters revealed that 100 are in favor of a certain bond issue. All right, that is a sample proportion. We got 432 voters, and 100 of them are in favor of the issue. A 95% confidence interval for the proportion of the population of voters who are in favor of the bond issue is what? Okay, well, again, we're looking for a confidence interval for the proportion of the voters that are in favor of the bond issue. So in our sample, we had 100 out of 432, which is 0.231. So that's the sample that we saw. That's the sample proportion that we saw. And every interval begins with a sample statistic. So we're going to begin with that 0.231. So I can immediately get rid of A, B, and C. They start off with how many How many? No. We're looking at the proportion of, not how many of. So now we're looking at D and E. Now the back part of a confidence interval is going to be our margin of error. Our margin of error is going to be our Z star when it comes to proportions times the standard error. And the standard error is going to be taking that 0.231, our p hat, 1 minus it, which is 0.769, divided by our sample size of 432. Now, both D and E have that exact same standard error. So now the only difference that's going to choose our right or wrong answer here is the Z star. What is the Z star for 95% confident? Well, we're going to go to our calculator to do this. Now, you can also go to a T table or a Z table to do this, but I'm going to use invert Z on my calculator or invert norm. So when I go to invert norm, it's asking me for the area. Now, most calculators, older calculators don't have this option for left, center, right, but mine does. But most calculators that don't have the option, they're automatically defaulted to left. So I just like to always use left. So if I'm 95% confident, that's 95% in the middle, 5% is left outside, but because of symmetry, that puts 2.5 at the top and 2.5 at the bottom. So I'm going to do 0.025 for that bottom area for I'm 95% confident, and that is going to be left, looking at that area at the bottom. Now, if you want to select center, if your calculator has the option to select center, you most certainly can, and then you would actually type in 0.95 for the 95% in the center. But this is going to get me my Z star, and it's 1.96. So that gives me the correct answer here of choice D. In this problem, it says in 2009, a survey of internet usage found that 79% of adults aged 18 years and older in the United States use the internet. A broadband company believes that the percent is greater now than it was in 2009, and it will conduct a survey. The company plans to construct a 98% confidence interval to estimate the current percent and wants the margin of error to be no more than 2.5 percentage points. So that means 2.5% or less. Assuming that at least 79% of adults use the internet, which of the following should be used to find the sample size n included? Okay, this is a classic problem that we're trying to solve for sample size based on a given margin of error. So let's start off with our margin of error formula. Our margin of error formula is going to be taking our Z star times the square root. Now, we got to also think real quick, there's a couple different formulas for standard error based on means or proportions, one sample, two sample. So hopefully this question is clearly talking about one sample. It's just said one sample. And it deals with proportions. How do I know it deals with proportions? Because it's talking about the percentage of people, and percentage is just another fancy word for proportion, that use the internet. All right, so inside the square root here, that's going to be our p hat times 1 minus p hat, all divided by n. And we're looking for this value, this margin of error, be to less than or equal to 0.025. That's the margin of error that they said they wanted to achieve, the 2.5 percentage points. All right, so now I just kind of have to fill everything in, and that's going to actually, and look at the choices. They're not actually asking me to solve it. They're asking me to set it up. All right, so first off, the Z star is based solely on how confident I want to be. In this case, 98% confident. So I'm going to go to my calculator, do an invert norm. If there's 98% in the center, that puts 2% on the outside, 0.01 or 1% on the left. All right, and that gets me 2.326 or 2.33. So there is my Z star. So I can immediately get rid of A and B because they have the wrong Z star. Now, what am I going to put inside here? Well, we don't even know yet because we haven't conducted our sample yet. So we actually don't know what our p hat is. That's the question. The question is asking what our sample size should be. And until we get our sample size, we can't actually get our sample proportion. And in a lot of cases, we teach kids when you don't know your p hat, just use 0.5 and 0.5. But this problem did tell us to assume that 79% of adults use the internet because that's what was true back in 2009. So why not use that number? So we're going to use the 0.79 and the 0.21 here. That's the opposite, all divided by the sample size n. And we want that total margin of error to be less than or equal to 0.025. Now we could solve this and actually determine what n is in order to produce this margin of error, but they don't really ask us to do that. So the correct answer here that we're looking at is choice D. E is wrong because it says it wants a 5% margin of error. We asks for 2.5%. C is a really good answer too. I almost get mad because I would give credit for C because it uses the 0.5 and 0.5. And then when we have no idea what p hat is, we typically tell kids to use 0.5 and 0.5. But in this problem, we do have this prior information, and it would make for a more accurate answer to use the 0.79. All right, this particular question says a manufacturer claims its brand A battery lasts longer than its competitor's brand B battery. 9 batteries of each brand are tested independently, and the hours of battery are shown in the table below. So we have all the results for brand A, the number of hours of battery life for each of the 9 batteries, and the same for brand B. Provide that the assumptions for inference are met, which of the following tests should be conducted to determine if brand A batteries do in fact last longer than brand B batteries. All right, now we're looking at the amount of time, the mean amount of time. Like what I could get from my brand A sample is the mean for brand A, and from my brand B sample, I can get the mean for brand B. Okay. Well, that means I'm clearly working with means, and when I'm working with means, I'm going to be doing a t-test. So I can immediately get rid of D and E because they say to use a 2-sample z-test. Z-tests are used for proportions, or if you know the standard deviation of your population. And when you're working with just 2 samples here, there's no way I'm going to know the standard deviation of my population. All right, now the idea here is I want to actually figure out that brand A does in fact last longer. So my null hypothesis would be that the mean for A is equal to the mean for B. There's no difference between these 2 batteries. And my alternative would be, again, that I do in fact think that A is longer or lasts longer than the mean for B. That means this is a one-sided test, because I only care about that one side where A is greater than B. A 2-sided test is when your alternative is a not equal to sign, and that would just be when I want to show that A and B are different. And that's clearly not what's happening in this problem. So this is a one-sided test. Now, why is it a one-sided t-test? Because when you're working with means, you typically have to use a t-test when you don't know the standard deviation of your population. And again, why is this a one-sided 2-sample t-test? Because I clearly have 2 samples, 1 sample from A and 1 sample from B. So the correct answer here is going to be choice B, a one-sided 2-sample t-test. 2 samples because I got 2 samples, 1 from A and 1 from B, and one-sided because my alternative is clearly that I'm just looking that A is greater than B. Now, this is not a paired test because remember, to be a paired test, your data has to be paired together. And there was no indication that this 88 and this 80 were paired together, or that this 80 and 77 were paired together. It never said that. It never explained a reason that I'd be pairing these together. So it's definitely not a paired test. It'd be a one-sided 2-sample t-test. All right, and this question says an experimenter conducted a 2-tailed hypothesis test on a set of data and obtained a p-value of 0.44. If the experimenter had conducted a 1-tailed test on the sample of data, which of the following is true about the possible p-values that the experimenter could have obtained? All right, now it doesn't even say if this problem dealt with means or proportions. I guess it really doesn't matter. But the idea is they did a 2-tailed test, which means that the alternative was a not equal to sign. So I'll just use the means to give an example here. So maybe the null was that the mean was 60. Again, just completely making that number up. And the alternative is that it is not equal to 60. Okay, that's awesome. Now, they tell us that, the p-value based on this 2-tailed test was 0.44, which means that whatever their p-value was, they doubled it and got the 0.44. So if we're thinking about that p-value, what that means is this. That means that there was 22% on that bottom and 22% on the top. And again, that's that 0.44 split in half. They doubled their p-value to get that 0.44. Now, most kids are going to say, oh, that means the answer is A. But no, the answer is D. And the reason for that is we never were told where our data came. Where was our sample? Was our sample on the low end? Now, if our sample was in the low end down here, then our p-value would be 0.22. Because if we said, all right, what's the probability that any other sample is more extreme than ours? Then that would be the 22% on the low end. Or same thing if it was up here. It would be the 22% on the high end. But here's the other idea. again, we don't know if our sample mean was high or low. We have no idea. So if our sample mean was right here, then the p-value could be that the probability of it being more extreme on the high side, which would mean anything above it on the upper side. And on the upper side of that would be 78%. So if we got 22% down here, then that means we have 78% in totality all the way above it. Now, it wouldn't make sense, or it would be strange to do a test where we have a value like that, but it's not out of the question. So it's kind of a weird question, and it stumped a lot of kids this year because most kids just jumped and said, oh, the answer is A, just cut that p-value in half and get 0.22. But again, we just don't know enough about our data. We don't know where we actually fell. We don't know if we fell on the high side or we fell on the low side. So again, if we fell on the low side, like right here, for example, and we were looking below, then yes, below would be the 22%. But we could also be looking above, and on above that would be the 78%. So that's why the correct answer here is D. All right, and this question says a randomized experiment was performed to determine whether two fertilizers, A and B, give different yields of tomatoes. A total of 33 tomato plants were grown, 16 using fertilizer A and 17 using fertilizer B. The distribution of the data did not show marked skewness, and there was no outliers in either data set. The results of the experiment are shown below. All right, so we're given all the information for fertilizer A. We're given the mean, 19.54, the standard deviation, 3.68, and the number of plants, 16. And then we're given all the information for fertilizer B as well. And the question says, which of the following statements best describes the conclusion that can be drawn from this experiment? Okay, so basically they want us to do the full significance test, but it's only a multiple choice question, so we don't have to do all of it. But just kind of running through it real quick, the null would be that the mean for A is absolutely no different than the mean for B. And the alternative would be that the mean for A is, well, simply not equal to the mean for B, because all we were trying to do was figure out if there is a difference. Is there, do A and B provide different results? Okay, well, we could go ahead. Again, we literally have everything we need to conduct the test. We're going to need to get the mean, or the difference between our two means. So we could just subtract the 19.54 minus the 23.39. We'd have to get our standard error for the difference, and that's a formula there as well. But the cool thing I want to show you is that this problem can be done very, very quickly using our calculator. So let me show you how to do this really quickly. So we're going to go to our calculator. We're going to hit stat, slide over to test. Now, which test is this? Well, this is going to be a test for the difference of means. We got two sample t-test. So we're going to scroll down here and do a two sample t-test. Now, let me walk through a little bit more of how I knew that. First, there's clearly two samples. I got the sample from fertilizer A, got the sample from fertilizer B. Okay, that makes it two samples. Why am I doing a t-test? Because when you're working with means in AP statistics, you're usually always going to be using a t-test. Because the only way to do a z-test for means is if you know the population standard deviations, which we don't. The only standard deviations given in this table here are that of our samples. All right, and when we go click on this, we're going to click on stats because we actually have all of the stats given to us. So first, I'm going to do A first. A is going to be my number one. So the mean was 19.54. The standard deviation for my sample A was 3.68. And the sample size was 16. Now comes the data for fertilizer B. The mean was 23.39. The standard deviation was 4.93. And the sample size was 17. Now, it's going to be really important that I select the alternative here of not equal to. It never said I'm looking at A is greater than B or B is greater than A. I'm just looking at that, are they different? So I'm going to select the mu1 is not equal to mu2. You never pull in AP statistics when it comes to a two-sample t-test. So select no there and hit calculate. And what this is going to do is it's going to give you the p-value and the t-score, everything you need. And it doubles it for you because we selected the alternative of not equal to. It's already doubled. We do not have to double the p-value. So the p-value is 0.016. Now, I could calculate that by hand if I wanted to, but why would I do that when the calculator could get that for me very quickly? Now, this is one of those weird p-values because if you use a 1% versus 5%, you could get different choices here. So let's kind of read what this says here. So if we look at A, it says that the p-value is greater than 0.15. That's false, so I don't want to select that one. B says the p-value is between 0.1 and 0.15. That's also incorrect. Let's see here. C says the p-value is between 0.05 and 0.1. That's incorrect. And D says the p-value is between 0.01 and 0.05. That is true. Our p-value of 0.016 is between 0.01 and 0.05. So it's probably going to be our answer here. Now, what does that mean? That means there is evidence of a statistically significant difference in the yields between fertilizer A and fertilizer B. So at the 5% level, I would reject the null. I would say that there is statistically significant difference in the yields between fertilizer A and fertilizer B because I'm less than 5%, but I'm not greater than 0.01. So that means at the 5%, I would definitely reject the null. Now, E says that the p-value is less than 0.01. First off, that's not true. Our p-value is not less than 0.01. So at the 1% level, I cannot say that there is statistically significant evidence of a difference in the yield. So the correct answer here is going to be D. So pretty good problem. It's just, knowing how to use your calculator can make a problem like this very quickly in terms of getting that p-value for you. All right, this problem says a large number of randomized experiments was conducted to determine whether taking a particular drug regularly would decrease the chance of getting a certain disease. Now, it's important to note it says a large number of experiments. We're not just talking about one experiment. They did a bunch of experiments to try to show that taking a particular drug regularly would decrease the chance of getting a disease. For each of the experiments, the drug effect is the difference between the proportion of people taking the drug who got the disease and the proportion of people taking a placebo who got the disease. If the drug had no effect whatsoever, which of the following experimental results would be anticipated? Now, let's just say we were conducting a test here. The null would be that the proportion of people who got that took the drug and did not get the disease is equal to the proportion of people who took the placebo. So these would be the people who took the drug, these would be the people who took the placebo, and that there's no difference whatsoever. And the alternative would be, well, the proportion of people who took the drug who got the disease is less than the proportion of people who took the placebo and got the disease, showing that the drug worked. But it's important to note that it said if the drug had no effect whatsoever, which means that the null is true. And that is that there's no difference between the proportion of people who got the disease on the drug and the proportion of people who got the disease on the placebo. So knowing all of that, which of the following must be true? P-values will be greater than 0.05 for about 95% of the experiments. Now, if your p-value is greater than 0.05, you're going to fail to reject the null. You do not have enough evidence to go with the alternative. And that's exactly true. That is what should happen, because if this is in fact true, remember, if the drug had no effect whatsoever, we should not reject it. We should be failing to reject the null. And if we have a p-value greater than 0.05, that's what we're going to do. So that's a good answer. 2 says there will be about an equal number of experiments showing positive and negative values of the drug effect. Yes, because if it's true that there is no difference, when you start to look at experiments, you know what? Experiments are going to vary. So sometimes you might see the drug being better, and the proportion of people taking the drug actually had lower results. But other times you might see the placebo group have lower results. The idea is that, if there really is no difference, you're probably going to see some experiments that show a positive effect and some that show a negative effect. And that's what's convincing you that, oh my gosh, I guess there's no difference between these two drugs, the drug and the placebo. So that's going to be true as well. 3 says when 95% confidence intervals for the population drug effect are constructed, those confidence intervals include 0 about 95% of the time. Yes, because if there really is no difference between using the drug and using the placebo, if we were to construct a confidence interval for that difference, we would have a 0 in that confidence interval, meaning that, well, there very well could be no difference. So all 3 of those are going to be true, which means choice E is correct here. And again, it's really important that you read that it says if the drug had no effect whatsoever. So if the drug really had no effect whatsoever compared to the placebo, we should fail to reject the null, which means we're going to have p-values greater than 0.05. We should get some of experiments that show a positive effect and some that show a negative effect, because there's really no difference. And if we conduct a confidence interval, we should get a 0 in it because there is really no difference. All right, hopefully that question made sense. It's another really, really good question about inference. So there's a chemical that's used in rocket fuel. People who live near a former rocket testing site are concerned that perchlorate is present in unsafe amounts in their drinking water. Drinking water is considered safe when the average level of perchlorate is 24.5 parts per billion or less. That's when it's safe. A random sample of 28 water sources in this area produced a mean of 25.3 parts per billion. Which of the following is an appropriate alternative hypothesis that addresses their concern? Now, the null hypothesis would be, nope, everything is okay. Then, oh my gosh, my handwriting is so bad sometimes. I'm sorry, guys. My null hypothesis would be that the mean is equal to 24.5, again, or less, because remember, it says that the drinking water is safe if it has 24.5 or less. Now, the alternative would be that it's more than 24.5, because then that's what they would be concerned, that the water is unsafe. They're not going to be concerned that it's unsafe if it's less, because less than 24.5 is safe. They're only going to be concerned that it's safe. They're only going to be concerned that it's unsafe if it's more than 24.5. So that's going to be our alternative hypothesis, choice D. Hopefully that was a nice and pretty simple one. All right, and this question says a physician believes that the exercise habits of East Coast adults are different from the exercise habits of West Coast adults. To study this, she gathers information on the number of hours of exercise per week from a random sample of East Coast adults and a random sample of West Coast adults. Which of the following might be an appropriate null hypothesis for this study? Now again, this particular physician thinks that there is a difference, but the null should always be that there is no difference between the average amount of time spent exercising for the East Coast adults and the West Coast adults. So we're going to be looking for a choice that says exactly that. Choice A says that the average number of hours of exercise for the East Coast is different than the West Coast. Now that would again be the alternative. We want the null, which says that they're the same. There's no difference. And that's exactly what B says, that the average number of hours of exercise per week for East is the same as it is for the average for the West. So there's going to be our answer right there, B. C says that the East is greater. D says the East is less. Those are all possible alternatives if that's what they wanted to use. And then E is kind of a really throwaway one. So the probability is 0.5 that an East Coast adult and a West Coast adult equal a, okay, just forget that one. That one's clearly going to be wrong. It doesn't even make sense. So B is going to be the correct answer because that's a good null hypothesis between two samples. And that would be that they are in fact the same. All right, here then this problem says in 2011, 17% of a random sample of 200 adults in the United States indicated that they consumed at least 3 pounds of bacon that year. In 2016, 25% of a random sample of 600 adults in the United States indicated that they consumed at least 3 pounds of bacon that year. Assuming all conditions for inference are met, which of the following is the most appropriate test statistic to use to investigate whether the proportion of all adults in the United States who consumed at least 3 pounds of bacon in 2016 is different than in 2011? Okay, so when we're creating our test statistic for the difference between two sample proportions, clearly working with proportions here, the numerator is going to be our difference. What was the difference between our samples? So the difference between our samples is going to be either 0.17 minus 0.25 or the other way around. It doesn't matter the order you subtract them. Now, if I look at the choices, all of them have that same numerator. Now, technically, it's going to be taking that 0.17 minus 0.25 and subtracting the null, that there is no difference, but obviously subtracting 0 is something that we just don't even need to do. So all of them have the proper numerator. Now, the denominator is where things get a little bit tricky. We need the standard error, but in a two-sample Z test for the difference between population proportions, you need to use standard error combined. Now, the standard error combined is using your p-hat combined. This is really important because when you do a test, we have that null that we assume that there is no difference. So if there's no difference, we combine them all together. So our p-hat combined, which we can abbreviate as p-hat C, is going to be taking all of them together, right? So that would be in 2011, 17% of the 200 adults. So I got to do some math there. 17% of those 200 adults would be 34. consumed that amount of bacon. And then in 2016, it was 25% of 600 adults. So 25% of 600 adults would be 150 people in 2016 that consumed more than 3 pounds of bacon. And that's out of the grand total of the 200 adults from the first sample and the 600 adults from the second sample. So that's going to be 184 divided by 800 for my p-hat combined. So 184 divided by 800 gives me a p-hat combined of 23%. That is what I should be using to calculate my standard error combined. So in that formula, I'm going to take the 0.23 times the 0.77, that's 1 minus it, divided by the 200 people from the first sample, plus the same thing, 0.233 times 0.77, divided by the 600 people from my second sample. That is the standard error I should be using. Now, if I'm looking at these choices, I really like choice A. I do. But it doesn't use standard error combined in a significance test. When you're conducting or when you're calculating that test statistic, you should be using standard error combined. This is standard error treating the two samples separately, and that's a great formula, but for a test, it's not what we want. So sorry, that's not going to be the correct answer. B is incorrect because it tried to do that, but it had the 17, the 83 under the 600 when it should be with the 200, and this should be the 600. But again, that's actually wrong anyway because we need to be using standard error combined. Now, what we want to do when we're using standard error combined, notice that the numerators both have the exact same. So what we could do is we could factor that out. So we're going to factor out that 0.23 times 0.77, and then we have 1 over 200 plus 1 over 600. So the correct answer here is going to be choice D. There it is right there. Now, what did choice C do? Well, they just took the average. They just took the average of 17 and 25, but you can't average proportions when they come from different sample sizes. That's not how you find the p-hat combined. This is how you find p-hat combined, what I did up here. That is proper. And then choice E is just using 50-50 for the p-hat combined. That's not correct as well. So again, a pretty tough question because it is one of those small little details of a two-sample z-test for the difference between population proportions that you kind of have to memorize. All right, in this question, it says an athletic director believes that more than 50% of the students in a certain school district exercise at least 3.5 hours per week. To investigate the belief, the director selected a random sample of 40 students in the school and found that 60% of the students in the sample exercise at least 3.5 times per week. Let P represent the proportion of all students in the school district who exercise at least 3.5 hours per week. Which of the following is the most appropriate alternative hypothesis to test the director's claim? Well, the athletic director believed that it's more than 50%. That's what he believed. He believed that it was more than 50%. So we want to choose the option that says more than 50%. That's going to be our answer. We don't want to choose anything with the 60% because the 60% was a sample proportion that came from 40 students. That is never going to be used in your null or alternative hypotheses. A sample proportion is used as evidence in step 3, actually calculating that test statistic in your p-value, but it's never going to be used in your hypotheses. He believed that it was more than 50%, so the null would be that it is 50%, and the alternative would be that it's more than 50%. So that's an easy question there. All right. An agriculture engineer selected a random sample of 30 farms in the United States to construct a 95% confidence interval for the mean size in acres of farms in the United States. The resulting interval was 367, 558. Which of the following is an appropriate interpretation of the 95% confidence level? Well, before I even read any choices, I'm 95% confident that the true mean size of acres of farms in the United States is somewhere between 367 acres and 558 acres. Now, is any of those choices say that? Well, go ahead and read them for a second. Well, of course not. None sound exactly like that. A says approximately 95% of the farms in the sample are between 367 and 558 acres. No, what are we talking about? 95% of the farms in the sample? No, that's just not correct language at all. B says 95% of all farm sizes in the United States are between 367 acres and 558 acres. No, I'm 95% confident, but not 95% of all the farms, right? 95% is about confidence and it's not about of the farms. That's not correct either. Now, C sounds pretty good. It says approximately 95% of all random samples of size 30 from the population will have a mean farm size between 367 and 558. But no, that's one thing a lot of kids choose because they like, oh, it incorporates the numbers from my interval and it talks about 95% of all random samples. But no, here's the idea. Every sample is going to produce its own interval. This is the interval I got, but a different sample is going to get a different interval. So trying to say that 95% of all samples are going to create intervals just like mine is completely wrong. So that one's wrong as well. Now, D says approximately 95% of all random samples of size 30 from the population will produce intervals that contain the mean size of farms in the United States. That is correct. That is beautifully worded. In fact, that's exactly what 95% confidence means. It's all about the many, many, many other possible samples out there of sample size 30 taken from the same population. And 95% of those intervals will contain the population mean. I hope mine is one of them. I hope it is. I don't know. I assume it to be. I'm confident it is. But again, 95% confidence, not talking about my sample. It's not talking about percentages of farms. It's talking about 95% of all random samples that are going to produce an interval that contains the true mean. And this is where a lot of kids get confused because we talk about interpreting an interval so much. So kids want to find a choice that interprets that interval, but none of them interpret it the way that it should be done. So that means the next thing is, well, does any of them correctly explain what 95% confidence means? And D nails it perfectly. All right, last question, this very long video, I know. A one-sample z-test for a proportion of the significance, let me start over. A one-sample z-test for a proportion at the significance level of 0.10 will be conducted for the following set of hypotheses. The null is that the true population proportion is 0.50, and the alternative is that it's less than 0.50. Which of the following is the probability of a type 2 error the greatest? Okay, so let's talk a little bit about type 2 error. So a type 2 error, the alternative is true. The alternative is true. But unfortunately, I failed to reject the null. So I keep a null hypothesis that is incorrect. So which of the following is the probability of a type 2 error the greatest? Now, this is the complete opposite of power, right? Power, if you recall, is doing the correct thing. The alternative is true, and you properly conclude that. So they're asking me to not have power, and that's bad. They want me to be bad. They want me to make a type 2 error. So I'm always thinking about the opposite of power. Remember, power is best when you have the big sample size. So I'm immediately going to go with getting rid of A, B, and C because those have the bigger sample sizes. When you have lower sample sizes, you have more room for making that type 2 error. Again, if I don't want to make a type 2 error, then I do want a bigger sample size. So I would choose A, B, or C. But this question wants me to figure out which of the probability has a type 2 error is the greatest. That's going to be coming from a smaller sample size. All right, now I have to determine what is correct, if the truth is 45% or if the truth is 35%. Well, I think of it like this. When the truth is further from the null, I have more power to see that. So if the truth was 35%, that's further from the 50% as opposed to 45%. That's actually going to give me more power to do the correct thing and go with the alternative. If the truth is 35%, that is way less than 50%. So I would hopefully see that and conclude that. So the correct answer here is going to be D. D has the smaller sample size, which puts me at a risk of a type 2 error, first and foremost, but it also has a truth that is close to the 50%. Now, it's still less than 50%, so I would hope I see that, but it's so close to 50%, maybe I don't see that. My sample size is kind of small, so again, sample sizes that are small vary more, so maybe I just don't get what I want to get, and that's going to cause me to have that type 2 error. So again, this is actually a really tricky question, and I hope I'm doing a good job of explaining it, but I always like to think about power. Power is making the correct decision. It's the complete opposite of type 2 error. Power is when it's less than 50% and I conclude that. And to get more power, I want a bigger sample size, I want a bigger significance level, and I also want to be further from the null. The further I am from the null, the further the truth is from the null, the more power I have. So in this problem, that's essentially asking me to find type 2 error being the greatest, which is the complete opposite of power. I want none of those things to happen, right? So I want a small sample size. That's why I got rid of A, B, and C. And I'm going to choose where the truth is close to the null, which means that maybe it's so close that I don't see it. So hopefully that made sense. It's a pretty good problem. All right. Now there was, a lot of questions about inference, and, I made a lot of them on purpose because there's a lot of them on the AP exam, and a lot of them are kind of tricky. And honestly, of all these questions I went over, I think only maybe 3 of them were pretty easy. The other ones, they do make you think really, really hard. So hopefully just hearing me review these questions is going to bring up a lot of the concepts that you need to know and study to prepare to do well in the exam.